And I think it's a really good section to move to because it talks about a new center, okay, a different intersection point of different segments for triangles. But it's very beneficial to talk about the altitudes today, maybe tomorrow, maybe the next day, depending on how many days we need to talk about this stuff. But it's good to talk about those now because the algebra that we do to investigate these altitudes and to determine equations for altitudes and determine the point where altitudes intersect is exactly the same algebra that we use to see where perpendicular bisectors intersect, to find circumcenters. Okay, so they're new segments, the new types of segments. They have new characteristics, but the algebra that we use to investigate those segments and to investigate those relationships and those characteristics is exactly the same algebra that we did yesterday on that assignment, the day before, and the day before that. Okay, so it's just a new geometric concept that we investigate using same algebra. The way I view algebra, and I think this is maybe probably the way a lot of people view algebra that teach it, is that they're your tools, they're your building blocks to investigate every other branch of mathematics. And if we're not very good at our algebra, we're not going to be able to investigate the branches of mathematics maybe the way we want to or we need to. Okay, so they're your guide to the rest of mathematics, and the more we can strengthen those, the better we're going to understand other aspects of mathematics. Okay, so my hopes are that you realize that we are doing the exact same thing we did yesterday, day before that, in regards to the algebra, but now with different segments. Okay, we need to talk about some definitions here. First one is altitude. Okay, so altitude of a triangle is simply the perpendicular segment from a vertex of the triangle to the line containing the opposite side of the triangle. Okay, segment from, or the perpendicular segment from a vertex to the opposite side. Okay, the line containing the opposite side. Give you a minute to write that down, and then we're going to kind of tear that definition apart, because there's a lot of stuff going on in that definition that rehashes things we've already talked about. Okay, and there's also a phrase in there that is extremely important to this definition. If we overlook that phrase, we're going to miss some of our altitudes in some triangles. Okay, so we got to look at that altitude definition in great detail. And then we're going to see a couple examples. So what I want to do is use kind of GeoGebra, because I think it's the best thing to do to be able to see these altitudes and to maybe draw comparisons to things that you already know. Okay, you guys know, what's the area formula for a triangle that you guys are most familiar with? 1/2 base times height, right? 1/2 BH, right? And I say the one that you're most familiar with, if you were to Google area formula for a triangle, you're going to get many area formulas. That's the one that we're most comfortable with. Okay? That's one you've learned maybe since like the 5th, 6th grade, whatever. Okay? But the H value that you guys refer to as height is actually an altitude. It's the length of an altitude that we're interested in. Now, it's only a portion of the altitude that we're interested in, so maybe that's why they call it the height, or they call it H instead of A. But altitude becomes a very important component to finding area and volume of a lot of different shapes. Okay, and just trying to draw comparisons about things that you currently know. Obviously, you guys know that formula: 1/2 base times height. But do you know? Like, has anybody ever been in an airplane? Okay, when you get to your like the highest flying distance off the ground, the captain comes on and says, "We are cruising at an altitude of yada yada yada." Okay, what does that mean? That's the height you're at. That's how far off the ground you are, right? Okay, so if my airplane is there, okay, so A is my airplane, and let's just do it this way. Let's say that is my ground. Okay? The altitude is the perpendicular distance from A to that line right there, correct? So the altitude that the pilot is talking about is that blue segment, correct? Does that make sense? Okay. And they say that's the altitude because that's the shortest distance from the airplane to the ground, right? Okay. There's a lot of distances, different distances from the airplane to the ground, but that's the shortest one. Well, when we talk about a triangle, is it fair to say that we could do this? And now we look at that purple triangle. What do you think that dotted line is for that purple triangle? It's the height or the altitude. Okay? Because it goes from a point, which is your vertex, perpendicular to the opposite side, or perpendicular to a line. Okay? And that then is that shortest distance. Okay? If we were, let's say that I had in front of you, I was going to take that triangle and cut it out of a smartboard. So you have that piece of plastic in front of you. And I ask you to set that on your table or your desk so that BC is resting on your desk, but A is up in the air. Okay? Does everyone kind of visualize what's going on there? Okay, if I did that. And I asked you to take a tape measure and measure how tall your triangle is. Would you take your tape measure and put it at A, and then put the other end of your tape measure at point B, and record that distance? And that would be your height, right? That would be your altitude. Okay. But could some people do this? Could I? Let's say that I have. Let's see if we can do this right. Another point in here. Don't worry about it. And we're going to rotate this thing around that point. Alpha. Create a slider. No. If I gave everybody that cutout triangle, okay, and actually let me do this, 0. Give everybody that cutout triangle. Some of you might, and I didn't give you any instructions on how to set it on your table. Okay. Some of you set it on your table like that with A up in the air. That make sense? Okay. Would some of you maybe set it where maybe you put C up in the air? Does that make sense? I know my triangles. Let's do it this way so my triangles aren't overlapping. Let's do it this way. Let's go. Would some of you set it that way? Does that make sense? And would another height? Okay, so if this is the table, this is the base, would another height be from C straight down? Is that how most people would act? If I asked you to measure the height of that triangle, you'd go from here straight down to your tabletop. Does that make sense? Can we visualize that? Okay. Well, that doesn't go to the side of the triangle, does it? Okay. Doesn't intersect the side of the triangle. Because, remember, by definition, the altitude said that it had to be a segment that starts at a vertex and is perpendicular to the opposite side. Well, if I go perpendicular to the opposite side, that ray right there will never be perpendicular to the opposite side inside the triangle, right? So what we have to do is we actually have to extend. We have to extend this side here, okay, and then we can be perpendicular to that. Does that make sense, everybody? Okay, so then the point that we were, not the point, but the distance that we'd be interested in, and if I've asked you the height, would be that distance. Okay, so some people could put your your triangle on your desk that way, and if I ask you the height of it, that dotted line would be what you're looking for, right? That would measure or resemble your tape measure, okay? That's where that idea, your altitude does not have to be on the inside of your triangle. That's where when we look at this definition, it says that it's the perpendicular segment from a vertex of the triangle to the line containing the opposite side, okay? Because that line may be the opposite side. We may, like we had here, this altitude goes to the opposite side, right? It goes to that segment on the opposite side. But here, it doesn't. So we have to extend that opposite side to the line that contains it, the line that that segment came from, and then we have that altitude. Okay? Could some people additionally maybe set their triangle on their desk so it looks maybe kind of like that? And you would see then that your altitude would be maybe a segment like that. Does that kind of make sense? Okay. So how many altitudes does every triangle have? 3. Okay. So when you do 1/2 base times height, okay, there is not just one B that you could use. You could use 3 different B's because there's 3 different H's you could use. Does that make sense? Okay. And then that turns into something, you guys talk about 1/2 B times H in 7th grade. You talk about it in 8th grade. You don't talk about it in the 9th and 10th grade. Okay. But in the 9th and 10th grade, we talk about it in respect to how it really doesn't matter which H you use, okay? When you choose an H, your neighbor might choose a different H, and their neighbor might choose a third different H, okay? But the H that you choose then dictates the base that you have to choose, right? Look at that first triangle, top right. If I choose AD as the H, okay, then BC has to be the B value, okay? Its length has to be B. If I look at this triangle here, okay, if I use C to F here as H, then the B value in my formula has to be that little distance. Does that make sense? Okay, so finding the area of a triangle, 3 different expressions you could write, 3 different equations, all using 1/2 base times height, but those numbers will change. But whichever ones you use, you should still get the same area 3 different times. Does that make sense? And we'll talk about that when we get to chapter, I think it's 10, 11. But to be able to do that, to be able to discuss that, we need to understand what altitudes are in this this section. Now, just think about these. We have 3 altitudes, just like we had 3 perpendicular bisectors, just like we had 3 angle bisectors. And those things started to intersect, right? What do you think is going to happen with our altitudes? They're going to intersect, okay? I'm trying to kind of mess around with one, a geometry, so you guys can mess around with it and see eventually the components of different types of triangles you can make. Okay, so this one's an acute triangle. Okay, and so this applet's not complete yet, but this is an acute triangle, and you see all these solid red lines, the thick red lines, are altitudes that are on the inside. So in regards to finding like 1/2 base times H, those would be the H's, okay? But if you extend those red lines forever, the extended entire red line is what they refer to as the altitude. Is that okay with everybody? And then H is a segment of that altitude. But you look at those, do those 3 altitudes, do they... We got the black lines now. Do those 3 altitudes intersect? Yeah. Okay. That point is, in this case, point D. It's going to be an important point here in a little bit. Okay. If I look at a different type of triangle, maybe I look at this triangle here. Okay. Now my altitudes are still the red lines. Okay. And the idea here, this is kind of what I'm trying to figure out with how to code this. But going from A prime to this side B prime, C prime, okay? There'll never be like an altitude in here because I'll never be able to get one of those green lines to be perpendicular to that side, right? So I have to extend this dotted line, okay? Extend B prime to C prime as that dotted line, and then I go from A prime perpendicular to that dotted line, right? So that would be an altitude. So that altitude shows up on the outside of my triangle. And if I extend it far enough, it will intersect this altitude that was actually on the inside of my triangle, and again, this second altitude that's on the outside of my triangle. But that point right there is still a point of concurrence. Okay, that's where all three altitudes intersect. What type of triangle do you think that is based off its angle measurements? Obtuse, right? Okay, so we have an obtuse triangle, and you can see that I think it's 110. It's gamma here. Okay, that's what that angle is. So there's an obtuse triangle. We had that intersection point is on the outside. When it was an acute triangle, look at all these angle measurements. That's obtuse still. When it's an acute triangle, all these angles less than 90. That point shows up on the inside, right? Let's see what happens when we have a right triangle. Where does that point show up? On the triangle, right? Okay. And we're on the triangle. At the right angle. Okay. Now this point of intersection, the point of concurrency for the altitudes has a special name. Okay. I've got too much stuff going on in that one, so let's go to this one here. That point of intersection of your altitudes is referred to as, you see it written there, the orthocenter. Okay, so that's something you want to write down. Okay, the point of intersection for altitudes is referred to as the orthocenter. Okay, as you're writing that down, just kind of think of maybe places that you've seen the word ortho before. Okay, orthodontist. Okay, and that has to do with your teeth, right? What's the orthodontist do with your teeth? Makes them straight. Okay, so when we make them straight, what they're doing, though, that makes them straight is that they're making them perpendicular to your gums. Okay? And when you make them perpendicular to your gums, make every tooth perpendicular to your gums, then aren't your teeth straight? Okay? So ortho means it has some type of component, some type of relationship to perpendicular. Okay? A lot of times in higher level math, the word orthogonal. Okay? The word orthogonal refers to planes and lines and rays and stuff having perpendicular relationships. Okay? You ever been to an orthopedic surgeon or heard of an orthopedic surgeon? Okay, they work with your skeletal system, right? They work with the, if I'm a person that kind of walks like this, right, leaning over a little bit, orthopedic surgeon's going to go in, do some surgery, and straighten me up, right? So now my plane of my body is perpendicular to the plane of the surface that I'm walking on, right? So wherever outside of this class you see the prefix ortho, it has some type of connection with trying to make things perpendicular, okay? Whether it's teeth to gums, spines and bones to ground, okay? Trying to make things perpendicular. The reason I give you that is because those are maybe associations that you could use when you get to a test and you forget everything. Okay, you think, okay, he's talking about orthocenters, he's asking a question about it, and I don't know, does that get made by angle bisectors, does it get made by perpendicular bisectors, does it get made by altitudes, does it get made by medians, okay? And if you see ortho, you can say, oh, it has to do with perpendicular something, okay? So maybe that narrows your options down to say, okay, it's either perpendicular bisectors or it's the altitudes, okay? And it wipes away the other two options. Does that make sense? So using those associations might help you in the situation in which maybe you forget something. Okay. Something that's really nice is knowing the fact that the orthocenter of a right triangle always shows up, no matter what right triangle you create, always shows up at the right angle. Okay. This is the one type of triangle. This is the triangle that you guys have used the most in like 7th and 8th grade, dealing with 1/2 base kind of type. You chose, a lot of times you just look at your triangle, say, okay, I want the left side be B and the bottom side be H, or in this case, the left side be B and the top side be H, or maybe you let this be H and you let that be B. Okay, it doesn't really matter because multiplication is commutative. You can flip-flop them. But the reason that works is because both of those H's and B's, they're both actually altitudes. And that's why it doesn't really matter which one you choose for H. because you see that the red lines are the legs of your right triangle, right? So in a right triangle, the legs of the right triangle are indeed the altitudes, okay? And your orthocenter then is going to show up at the right angle, okay? So I'm going to ask you questions in the near future, and that future is getting nearer and nearer. Let's say that I give you that triangle right there, and I ask you, find the orthocenter. Where's that? What's that be? It's at -8, 1, right? You know the order pair automatically just by using that fact, right? Now, you could go through all the algebra. You could go through the 10, 15 minutes of algebra that's going to take to do that, but you're going to find out that it's B, okay? So knowing that fact is a little bit easier. Where's the circumcenter of that one? Good, the midpoint of AC, okay? So what, -4, 3, right? Okay? So there's a lot of algebra that can kind of get simplified when we understand these facts about certain points and where they show up on certain types of shapes. But what happens if it's not a right triangle? What happens if I do something like that? The orthocenter is no longer at B or C or A in this case, so we have to have a method for finding it. Okay? This is why I like this section, and why I want to talk about altitudes today and not medians, is because in the event of trying to find that orthocenter with coordinate geometry, it's the exact same algebra that we've been doing. Okay? And I'm actually going to cut and paste this real quick out into another program. I might actually already have it in. Yeah. All right. So I want to find the orthocenter of this triangle. Okay? And we have to understand the definition of an orthocenter to be able to do this. But it's going to be the same algebra as before. We're going to try to find equations that represent these lines, these altitudes, and then we'll use a system of equations to see where those two lines or three lines intersect. Okay? So I'm going to think about maybe from that point S to perpendicular to the opposite side. So let's go perpendicular over here, and maybe I'm just going to ballpark it. That kind of looks perpendicular. Okay? So just so I can talk about it a little bit easier, let's color that line. Okay? So I want to find the equation of that red line. Well, if I want to find the equation of any line, no matter where it's at in the xy plane, I'm going to try to use this thing. Okay, we'll see exactly how maybe that does fail us here in a little bit, but 99.9% of the time we will use that formula. Okay? Well, with that formula, which is what we've been doing, we always need a point that we know is on the line we're trying to find the equation for, right? Now, how many points are on that red line? A lot, right? There's an infinite number on that red line. And you don't know any of them except for one. What's the one that you know for certain needs to be on that red line? You need to know S. Okay? You know for certain, because this red dotted line, and we're trying to make that the altitude. Okay? And we know by definition the altitude goes from a vertex perpendicular to the opposite side. That's a vertex. So we know at -2, 2, that point is on the line. So that's your x1, y1. When we did circumcenters, your x1, y1 was the midpoint, right? This should actually be a little bit less work, because we don't have to go through the midpoint. They're going to always provide me the three vertices of my triangle. Okay? So x1, y1. Okay? Now I need the slope of the red line. Well, the relationship is that the slope of the red line should be the what of the blue line. Opposite side reciprocal. So if I find the slope of Q to R, which Q is at 5, 2, right? And R is at 0, -4. If I find the slope of that segment QR, 2 minus -4 over 5 minus 0 gives me 6/5, right? So Q to R's slope is 6/5. So what is the slope of this red altitude? Negative 5/6. Okay. So what's nice now is that we've got everything we need. We've got the M and we've got the x1, y1. So we're going to plug that stuff in. You know, y minus 2 is equal to negative 5/6. X minus negative 2, so it becomes plus 2. Just be careful with that minus and negatives. I've seen a lot of people in last night's homework do everything right, but make that a minus 2 instead of a minus and negative 2, and that throws everything off, obviously. Go ahead and start multiplying and combining like terms. So if I multiply that negative 5/6 through, I get negative 5/6x. Okay, now 5 times 2 is 10, and it's going to be negative 10. And then 6 times that denominator of 1 would be 6. Okay? What's that reduced to? What's 10/6 reduced to? 5/3. So it's going to actually be minus 5/3. I like to reduce right away. If you want to do it at the end, that's fine. But now I'm going to have to add 2 to both sides, right? So negative 5/6 x minus 5/3 plus now 2. If I want to add those two things together, I need a common denominator, right? What's the common denominator going to be here? 3. So this number is going to go to 2 times 3 up top, right? So that's a 6 up top. So now I've got negative 5/3 plus 6/3 gives me what? 1/3. So my equation of my red line is y equals negative 5/6x plus 1/3. That's the equation of that red dotted altitude. Okay. Now I like to have the picture in front of me because the picture, if I take time to kind of make a, I'm not saying a perfect picture, but try to maintain some type of scale, then this information should kind of be reflected in my line, right? Y-intercept. What's the y-intercept in that equation right there? 1/3, right? Does that line look like it crossed that 1/3 from the y-axis? Okay. Negative 5/6. Is my slope of that red line negative? It goes down from left to right, right? And negative 5/6 is pretty close to 1, right? Does this slope look like it's pretty close to down 1, over 1, down 1, over 1? That's not exact, okay? But negative 5/6 is not exactly 1, okay? But it gives me a ballpark idea that I've probably done things correctly here, right? And that's the kind of thing that I want you guys to be able to recognize and look at when you're on, you know, ACTs and in-course exams. Can we have a ballpark idea before I circle a bubble or type something in? Do I have a rough idea that I know I've done the work right? Okay. So we know. I should write down that in red. We know that equation of that red line is negative 5/6x plus 1/3. Okay. Now we could, and I'm trying to show you some shortcuts here to use when you can. We could find the, you know, maybe that looks to me like the altitude from Q to SR, right? And we could go through the exact same process of using Q as x1, y1, and using the slope of S to R and its opposite side reciprocal to find the equation of that green line, right? Make sense? Okay? And that would be enough. Now, all you need is 2 of these things, and that'd be fine. Okay? But I think there's an easier way here. If I look at that line right there, what type of line is it? It's horizontal, right? Okay. And horizontal lines, think about this. If I try to find a slope here, this is negative 2, 2, and this is 5, 2. If I try to find a slope, what do you get when you subtract your logs? 0. And the run is 7, right? I don't really care what the run is. I know it's going to be some number. It's not going to be 0. If it was 0, that would mean the 2 points were actually the same point. If my x difference and my y difference are both 0, that means the points are the same. But that's a number. Whatever that number is, what's 0 divided by any number? 0. So my slope of a horizontal line is always 0. Okay? So think about that. So I had 0 over 7 as slope, right? Yeah. 0 over 7. Okay? What's the reciprocal then? 7 over 0. What's the problem with 7 over 0? It's undefined. So if I'm trying to find, right now, if I'm trying to find the equation of that black dotted line I just put in there, it doesn't have a slope that I can use. And that's what I was saying earlier, is that this thing here works 99.9% of the time, except when we're trying to find the equation of a vertical line. When I want to try to find the vertical line, we need the slope here. Slope is undefined. Undefined means it's not a number. It does not have a numerical quantity that we can use to represent it. Does that make sense? Yes. So I couldn't be able to distribute all that stuff, right? Yes. So does anybody know how I write the equation of that black dotted line? It still has an equation, and we're not going to use the word. Okay, careful. You're on the right track. If I look at those points, do the y values of all those points on that line change? Yes. But does the x value of all those points on that line change? No, they're all what? 0. So when I want to define that line, I want to talk about a rule for that line. We simply say that line is x equals 0. Any vertical line is x equals then the number that line passes through on the x-axis. So if I had something like that line right there, what would you call that line? X equals 5. Okay? Now what's nice about this is that this is still a system of equations. It's just a extremely simple system. You already know what x is. You don't have to do any work here to solve for x. They're telling you it's what? 0. And when you plug 0 into this, what do you get for what? 1/3. So 0, 1/3, that is your ortho center. And look over here. Does that look like where my dotted lines intersect? 0, 1/3? Okay. So my hopes are that you kind of use that shortcut if you can, because if I were to use that green one that I had in here, I deleted it, but if I would have used that green altitude, I would have still found the exact point 0, 1/3, but the amount of work that I had invested in that would be a lot more than what we did. Does that make sense? Okay. What if I had so like this here? Let's say if that's 4. That line would be, what would the equation of that red line be? X equals 4. Okay? Because every point on there has an x value of 4. What would that blue line be? Y equals 2. Because anywhere on that, the y value is always going to be 2. Okay? We call those types of lines, vertical or horizontal lines, we call them constant. Okay? Because the x value is constantly 4, right? It never changes. The y value of that one is constantly 2, right? Never changes. The other ones, like 2x plus 4, or 2x minus 1/2, or whatever, those change. Those are variable, right? Okay? But these do not change at all, and that's hopefully you guys recognize that that's not a difficult concept, right? But it's almost too easy that we make it hard a lot. Okay? I have college students, okay, whether I teach it here or I teach it on campus, that struggle with that concept because it's almost too easy for us, okay? And we try to overcomplicate it. Please commit that to it. It's a huge component of a lot of mathematics that we do. If we can use vertical and horizontal lines to express altitudes or medians or perpendicular bisectors, that's the best thing to do because it eliminates a lot of the algebra work. Okay. I sent you guys a homework assignment earlier today.